See, we'll start from the beginning. So what is the dot product? How many types of product we have? Vector multiplication.
Dot product and cross product.
Dot product and cross product. What is A dot B?
AB cos theta.
A dot B is AB cos theta. Okay. Now we have I, J, K are said to be the unit vectors along x-axis, y-axis, and z-axis. What is I dot I?
1.
I dot equal to J dot J equal to K dot K equal to 1. Why? Because theta equal to how many degrees there?
0 degrees.
Theta equal to 0 degrees. And theta equal to 0, cos 0 is
1.
1. Very good.
Mm.
Suppose if when we go to the I dot J equal to how much?
0.
0. Why 0? Because cos 90 equal
90
to
degrees.
0.
cos 90 equal to 0. Very good. Now we have work. Okay, work energy theorem. What is the statement of work energy theorem?
Change in kinetic energy is equal to the work done on it.
Change in kinetic energy equal to work done. Okay, that is work energy theorem. So what is the formula? Kf minus Ki is equal to work done. W. Okay. Next, after that, we have work. What is the definition of work? Definition of work. Work is the product of
Force and
of
displacement.
force component in the direction of the displacement and displacement. Okay. So F cos theta into D equal to FD cos theta. And what is the dimensional formula for work? Dimensional formula for work. ml square t to the
minus
L square t to the power minus 2.
ml square t to the power of minus 2. And the unit of work is joules or kg meter per second square. And what is the CGS unit of work or energy? CGS unit of work or energy? Quick.
Dyne.
Dyne, not dyne. Dyne is the unit for force.
Erg.
Erg. Okay, one erg equal to how many joules? It's okay, sir. One erg equal to how many joules? 10 to the power of minus
10
7.
raised to 7 minus 7.
Minus 7. 1 joule
Yes,
equal to 10 to the power of 7 erg, or 1 erg is equal to 10 power minus 7 joules. So that's valid. After that, we have work done by variable force. Okay. So when we don't have a constant force, we go with when the force is variable. In that case, we use work done by variable force. So how do we write W equal to integration of fx dx? So from where to where? Xi to xf. Is that clear? So now we'll do a numerical on that also. Now, after that, we have there is mechanical energy. What is the classification of mechanical energy? Potential energy and kinetic energy. Again, in potential energy, what is potential energy?
energy possessed by a body due to height or
Very good. Energy possessed by the body due to the height or due to the position or due to the shape. If it is due to the position, it is what is the
gravitational potential energy.
gravitational potential energy. If it is due to the shape, then
Elastic potential energy.
Elastic
very
potential
good.
energy.
Now, what is the formula for GP, gravitational potential energy?
MGH.
MGH. Formula for elastic potential energy?
Half kx square.
Half kx square. And what is kinetic energy?
Energy possessed by a body due to its motion.
Very good. Energy possessed by the body due to the motion is known as kinetic energy. That is half mv square. Do you know why I am revising every day? Yes, Diyali, Devika. Are you people referring the notes every day? Yes or no? Okay, anyways. Anyways, okay. So kinetic energy. So the formula is half f square. Okay. Next one. After that, we have what is law of conservation of energy?
Energy can neither be created nor be destroyed, but can be transformed from one form to another.
Very good. Energy is neither created nor destroyed, but can be transformed from one form to another form. That is law of conservation of energy. Now, what is the definition of spring constant? What is the definition of spring constant?
The stiffness or hardness.
Yeah, very good.
Yes.
Stiffness or hardness of the spring is said to be spring constant. What is the unit of spring constant? What is the unit of spring constant?
Yeah.
Yes. Definition of spring constant. Newton per meter. Spring constant, stiffness or hardness of the spring, or also measured in, also known as Newton per meter. Okay, Newton per meter. Okay, now next one. Okay, so what is the formula for elastic potential energy? Formula for elastic potential energy.
A square.
After x squared.
What is x over there? X is what? X is
Displacement.
compression or extension. Compression or expansion or extension, we say. Next is, what is the formula? Suppose at the extreme points, what energy is maximum? At the extreme points, what?
Potential and
Very good. Potential energy. At the mean position?
kinetic energy.
Kinetic.
Kinetic.
Now, I want to bring the relation between velocity and the displacement. What is the relation? V equal to Vm equal to under root of K by M into Xm. Okay? K by M into Xm. Clear? Now, next one. What are the different forms of energy? What are the different forms of energy? Anyone? What are the different forms of energy? So we have heat energy, electrical energy, nuclear energy, chemical energy. Yeah. What is heat energy? Energy possessed by the body due to the vibrating particles.
Vibrate.
Next, chemical energy, energy stored in food, fuel, and drinks. That is chemical energy. In that we have exothermic, endothermic. If the energy is given out while the reaction is happening, that is exothermic. If the energy is taken in, that is endothermic. And next one is what? Nuclear energy. Energy possessed by the body due to the stored in the nucleus of a radioactive element. Okay. Next one is what? Mass energy equivalence relation is what? Mass energy equivalence relation. So mass energy equivalence relation. E is equal to mc square. Okay. Next is power. What is power?
Rate of doing work.
Very good. Rate of doing work. So power is equal to, we have on the board. Power is equal to work done by time. Power P is equal to F into V. Now next is measured in watts or joule per second or kg meter square per second power minus K. And ml square T power minus K. And 1 HP value is 746.
46.
And 1 kilowatt hour is equal to 3.6 into 10 to the power of 6 joules. Okay. Clear?
Yes, sir.
Now,
Yeah.
okay, now we will go to the last part of the lesson. That is about the collisions and conservative and non-conservative forces. So by that we can finish off this lesson. Okay. Now First, we'll start with conservative forces. Okay. Conservative forces means if the work done uh, does not depend, if the work done does not depend on the path followed by the body, on the path followed by the body, then that is known as conservative force. Example is what? Gravitational force. Example is gravitational force. Next is elastic and electrostatic force. Elastic force and electrostatic force. Electrostatic force. Okay, if the work done does not depend upon the path followed by the body, how it is happening that it does not depend. Okay, how you are bringing from one place to another place, that body. So the path doesn't matter. That is known as conservative force. Okay, the next one is that is independent of the path, and the second one is non-conservative. If it depends on the path, non-conservative force. Non-conservative force. If the work done depends upon the path followed by the body. If the work done depends upon the path followed by the body, then that is non-conservative force. Example for that is frictional force. Example for that is frictional force. Frictional force depends upon the path followed by the body. Okay, so these are the two types of forces. Next one, we'll start with collisions. Is it clear, girls?
Yes, sir.
Yeah. Okay. Now, now we'll start with collisions. Clear? If the work done does not depend upon the path, that is independent of the path, that is conservative force. Depends on the path, non-conservative force. Now, next is collisions. Collisions. In collisions, we have when two bodies interact. When two bodies interact, it is termed as collision. When two bodies interact, it is termed as collision. Okay, so we have when I say head-on collision or central collision, we generally take head-on collision, or central collision, or central collision. Head-on collision or central collision. It means what? Colliding bodies move along the line during their sunrise. Move along the line joining the centers. Colliding bodies move along the line between the centers. Then that is known as head-on collision. Now we have perfectly elastic collision and perfectly inelastic collision. So there are two types of collision. That is perfectly elastic collision. Second one is perfectly inelastic collision. Perfectly elastic collision and perfectly inelastic collision. So perfectly elastic collision means if both energy and momentum and energy are conserved. Okay, first copy this, then we'll go quickly to the next concept. So when two bodies interact, okay, so here what will happen? Suppose this is M1, whose initial velocity is U1. This is M2, whose initial velocity is U2. This is at the time of collision. M1 and 2. So momentum transfer takes place. After that, they both are moving with a different velocity. Here M1, M2. So this is V1 and this is V2. Okay, V1 and V2. Clear? Clear? Shall I go ahead now?
Yes, sir.
Okay. Now,
One second. The last point for head-on collision. 1 second.
now, so perfect elastic collision. Perfect elastic collision. If both momentum and energy are conserved, if both momentum and energy are conserved. Okay, both energy and momentum, the total, or we can say total energy before collision is equal to, or we can say total energy before collision is same as the total energy after collision. Then that is known as uh, elastic collision. Okay, now next one is perfectly inelastic collision. Perfectly inelastic collision. So what is that? When two colliding bodies, stick together after collision, after collision. Stick together after collision. Then that is known as inelastic collision. Okay, here what will happen? Momentum is conserved, but here momentum is conserved, but energy is not conserved. Momentum is conserved, but energy is not conserved. Okay. So when I say an perfectly elastic collision, that I'll explain now. Okay. So these are the two types of collision. Means best example is what? So motion of a bullet embedded in a target. Example for this is motion of a bullet embedded in the target. Means the bullet goes and gets embedded in the target, and both together they move. The block and the bullet both together move with a constant velocity, some velocity. That is known as perfectly inelastic collision. Okay. That is known as perfectly inelastic collision. Okay.
Yes, sir.
Any doubt, girls?
No, sir.
Okay. Going ahead now. Can I raise it?
Yes, sir.
One second. See, in perfectly inelastic collision, what we do is, some example, there are two trolleys, trolleys, which are outside the supermarket. Two trolleys are there. They both are moving. What happens? The second trolley, you push it. So this will go and get stuck into the first trolley, and they both move together with the same velocity. So that is known as example of inelastic collision. Means both M1, M2 will go together after collision. They stick together and they move with a common velocity. That is known as inelastic collision. Clear? Is it clear?
Yes, sir.
Okay. Now, I'm going with the derivation of elastic collision. Elastic collision in one dimension. Elastic collision in one dimension. Elastic collision in one dimension. So here we have, this is M1, whose initial velocity is U1. This is M2, whose initial velocity is U2. This is at the time of collision, M1, M2. Now this one, M1, M2, and this is V1 and V2. Now, how many variables are there? Total 6 variables. 1, 2, 3, 4, 5, 6. 6 variables are there. So in the problem is, they will give 4 variables. Only M1, M2, U1, U2. They will ask you to calculate V1, V2. For that, we are doing derivation now. Out of 6 variables, only they will give 4 variables in the problem, in the numerical. 2, they will ask you to calculate V1, V2. So the derivation in the textbook is little tricky. So I'm not using VIF. In the textbook, he has given like this: VI1, VI2, VF1, VF2. So I'm not going to take all these things. F for final, I for initial, like that it is given. So I'm not going to take, I'm just taking U1, U2, V1, V2 to make it very simple. Okay. Anyways, they are not going to check all these things in the exam. They just wanted to look at the way how you do it. Okay. Now, what I'm going to do, because it is elastic collision, both momentum and energy are conserved. So what will happen? So the formula is what? M1 U1 plus M2 U2 equal to M1 V1 plus M2 V2. And energy is also conserved. So that is half M1 U1 square plus half M2 U2 square equal to half M1 V1 square plus half M1 M2 V2 square. Okay. M2 V2 square. So this is the first formula. Now what we are going to do now? We are going to bring, so suppose this is equation number 1, equation number 2. Okay. Now what I'm going to do, I'm from 1. Okay, I'm going to modify 1 now. So when I modify 1, what do I get? I bring all M1 terms together, M2 terms together. Okay, so what happens now? M1 U1 minus M1 V1 equal to M2 V2 minus M2 U2. Now take M1 common. So what will happen? M1 into U1 minus V1 equal to M2 into V2 minus U2. Is it clear, girls? Is it clear?
Yes, sir.
Let it be equation number 3 now. Now, from 2, equation number 2. What I'm doing, the same way. How I have brought M1 terms together, the same way I'm going to do with this also. Half M1 U1 square minus half M1 V1 square equal to half M2 V2 square minus half M2 U2 square. This is a simple way I'm doing. Please don't follow different books for this. Okay. Don't follow even the textbook for this. Just in a simple way I'm trying to do it. Because it is a lengthy derivation of 2 pages. Because I'm trying to make it little simple. Now, so it is half M1 is taken common here. So what will happen now? U1 minus V1 square. U1 square minus V1 square equal to half. This is M1, half M2. M2 into what? V2 minus V2 square minus U2 square. V2 square minus U2 square. Okay. Now what will happen? So half M1, that is what? Okay. So half this will go away. Half and half is cancelled. Okay. So I'm left with what? M1 U1 square minus. Can I write this? Can I open the bracket now? A square minus B square. What is the formula of A square minus B square? What is the formula?
A plus B into A minus B.
Can you say it again?
A plus B into A minus B.
A plus B into A minus B. U1 plus V1 into U1 minus V1 equal to what? M2 into V2 minus U2 and V2 minus plus U2. Okay. So let it be equation number 4. Now divide 4 by 3. So what will happen? U1 plus V1, U1 minus V1 divided by M1 here. I'll write M1 also. 4 by 3. 3 is here. M1 into, see, this is 3. U1 minus V1. U1 minus V1, which is equal to what? M2 into V2 minus U2, V2 plus U2. Okay, divided by M2 into V2 minus U2. So what will happen? This and this will go away. This and this will go away. So this and this also will go away. This and this also will go away. So what you are left with, U1 plus V1 equal to V2 plus U2. You are left with this one. So now what I have to find out? I want to find out. 1 second. Yeah, so so I got this M1 V2 equal. I got the relation. I want V2 now. So what I'm going to do now? V2 implies V2 equal to how much? U1 plus V1 minus U. This is V2 value. This is V2 value. Now, once I'm done with this, I'm going to substitute in the first equation again. Okay, I'm going to substitute in equation number 1. So now let it be equation number 5. Now substitute 5 in 1. 5 in, where is that equation? Yeah, I will substitute in 1. 5 in 1. So what will happen now? M1 U1 plus M1 M2 U2 equal to M1 V1 plus M2 V2. What is that? U1 plus V1 minus V2. So what will happen? M1 U1 plus M2 U2 equal to M1 V1 plus M2 U1 plus M2 V1 minus M2 U2. Okay. So what will happen now? M2 U2